Let's take a look at a simple harmonic motion example. So harmonic is something that oscillates. Here we have a spring that's hanging with a mass at the bottom, and the position of that mass is based on this equation right here. 3 times the sine of 2t. T is seconds, s is in inches, and we want to know what's going on with the velocity and the acceleration when t equals 2 seconds. So here below I have a graph of the function, and this isn't, again, what the spring is doing. This isn't a spring here. This is just the height of the mass at any particular time. And at 2 seconds, I graph the tangent line to go with it. We'll look at that more in just a second. Let's take a look at what the spring situation looks like. So here's my spring hanging with the mass at the bottom here. And I'm going to hit play at the bottom. And what we're going to record here is what is the height of this mass over time. So we're going to watch a wave spread out because this height oscillates. First, it's low because of the mass. We pull it down. Equilibrium here is at the x-axis. So we're pulling it from its equilibrium. When we let go, it's going to spring back up and then down. Let's watch. And hopefully you see that the mass is speeding up and slowing down. It's moving slowest right before it switches from up to down or down to up. And it's moving fastest as it passes through its equilibrium. So the physical situation is this spring, ignoring any friction, is just going to bounce up and down like that forever. Friction will slow it down, but we're ignoring friction here. Equilibrium, if we don't pull on the mass, it's just going to sit right there. But we pull it down, we let go, and then it's just going to bounce up and down. That's what we have here. Let's take a look at this Desmos version of our function. So starting at time equals 0 here, the mass oscillates. So in this case, maybe we let it go right here, and then we start counting right here, and the mass goes up and the mass comes down. Now, right now, at this particular point, 2 seconds into this situation, I found the derivative here. Derivative of 3 sine of 2x is 6 cosine of 2x. If I plug in 2, I get a slope, a speed of about -4. Now, earlier, the speed, like right at its equilibrium here, was around -6. So here I have a speed of -6. Then the speed is changing to like -4-ish. And then the speed right before it turns around, right, there's an infinitesimal pause, and then all of a sudden it starts to go up. So here's the thing to notice here. If my speed goes from -6 to -3 to 0 to 1, my speed is increasing. Change in speed is acceleration. So what we should find is when we calculate the acceleration around 2 seconds, it's a positive acceleration. Even though this thing is moving in a negative direction, it's got a negative velocity, the velocity is decreasing. Change in velocity is acceleration. So let's calculate the acceleration, see what we get. So acceleration for some value x here. So I have to take the derivative of my velocity function. The 6 just hangs out, times derivative of the cosine, which I'm going to put a parentheses, that is negative sine. Chain rule says leave the 2x alone at first, and then multiply that by the derivative of 2x, which is just 2. So that would be -12 if I clean that up, sine of 2x. I'm going to turn that off. I don't need to see the graph, but I wanted to calculate what is the acceleration at 2 seconds. And let's set this back to 2 up there. Oops. And so I want to just ask, what is a of 2? Or since I set t to 2, I'm just going to say what's a of t. And I can say I have a positive acceleration there. And that's because my velocity went from -6-ish around here to -4 around here to 0 right before it turns from going down to bouncing back up. So my velocity is increasing. Change in velocity is acceleration. That's positive acceleration. Hope this was helpful understanding what's going on physically behind this problem.